So you code up a belief network and it doesn't work. What do? The reason we got to go through that is because it's probably going to happen, right? I mean, that's just the first thing that happens when you go through any assignment is your first implementation has problems. So you need some kind of a unit case. Here's one. This is a pretty simple unit test. You could use your graphical model to code this up and see if it works. What if it doesn't? How do you debug that? So I hope it works because it should. You will eventually get these same values. Of course, it depends on a couple of factors. So how do you achieve those numbers? What you do is you do Gibbs sampling for a while. So we sample the network and you're going to get a bunch of values and they're not going to be exactly those values. Where do those numbers come from? Well, what you have to do is you sample for a while and then you take all of your samples and you throw them in the garbage. This is called burn-in iterations. The reason for it is because, remember, it takes a little while before we converge. Remember this picture somewhere? Okay, this is the stuff we need to burn in and throw away. And then by the time it converges, then we want to take a whole bunch of samples. Now in this picture, it's completely static, but when it's a distribution, they'll still be jumping around, but eventually they'll be jumping around the correct distribution instead of the not correct distribution. So you sample all the nodes in your network, sample this one, sample that one, sample that one, sample that one, and after about 1 million iterations, you start over and you start sampling again. And then you sample, 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 and this time you collect the values at every node. So let's suppose we're interested in that orange node. We see what values come out of that orange node, and maybe we collect 1,000 of them. We sum them up, we divide by 1,000, and that's the mean value coming from that node, right? And the mean value coming from that node should match the numbers that are the correct values for the distribution you're doing. So in this case, we have A, B, and C. That's kind of meaningless as compared to that rain one, which was slightly meaningful. In this case, though, A is 2/5. What does that mean? It means you'll get a bunch of values in which it will say true. Each of these nodes are Boolean, and it'll say true 2 out of 5 times, and it'll say false 3 out of 5 times. So you will never get the number 2/5 coming from an A. You'll just get true, true, false, 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 true, true, false, 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 true, false, true, false, true, true, false, 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 true, true, false, false, like that. Okay. You collect some stats, eventually you report the mean, and the mean should converge to exactly 2/5. And by exactly, I mean after infinity iterations. Of course, you will not have infinity iterations, therefore you're going to be content when you get some number that is within plus or minus 0.01 of 2/5, or even 0.1 of 2/5, because truthfully, we don't have all of eternity to run here. Okay, but it really should, if you start over and run it again, you shouldn't consistently be higher than the number. It should, on average, be correct. Does that make sense? Okay, that's how you know when you're correct. So you code up this Bayesian graphical model, and notice I have the correct answer right there for you. So you do a whole bunch of burn-in iterations, and then you do a bunch of sampling iterations, and you take the mean. In fact, I actually recommend you take the median rather than the mean, because the median is more robust to variance, and you'll get closer to the right value with median faster than you will with mean. So there you go, do median. Let's suppose you do that and you don't get the right answer. How can you find the bug in your graphical model? In fact, before we do that, do you guys know how to calculate a median efficiently? Maybe that's a harder question. Okay, how do you calculate the median? You collect a bunch of numbers, you put them in a list, you sort the list, you take the number of items in the list, you divide by 2, you see what value is at that location, that's the median. Technically, if there's an odd number in the... No. Technically, if there's an even number of items in the list, you actually find the 2 values on either side of the midpoint, and then you average them together. That's a convention, not necessarily a true thing to do. In this case, presumably the list is long enough that you can just pick either one and it should be close enough. I think that's kind of a silly thing to do, but That's what Excel will do. So if you're trying to match somebody else's numbers in order to say you've done median correctly, you have to average 2 in order to get median for an even number of items. The problem with that is you can calculate the mean in order n time, right? If there are n items, you can calculate in order n time. If there are n items, how long does it take to compute the median? The optimal answer is order n. You can actually do median as fast as the mean, but most people do it in n log n time because they're used to sorting and all of that. So here's the question. How do you calculate the median in order n time? What's that? A good sort function? There do not exist any sort functions that can beat order n log n time given the assumption that it operates based on pairwise comparisons. There are versions of radix sort that can beat n log n time, but you have to know extra things about your data, specifically how many buckets they go in and some other things like that. They have something about the distribution. So the answer is what you want to do is partially sort the list. The only thing you need is that middle point needs to be at where it would be if the whole list were sorted. Does that make sense? Okay, this is not really essential learning. This is more because you're grad students and you want to know everything. But this is a big long number line. Pretend there's a whole bunch of data points scattered along it. Well, whatever number happens to be right here is the median, right? So you really need whatever value would be there if the whole thing were sorted to be right there. But if it happens that this value and those values are swapped and are out of order, who cares, right? So how would one do that? Turns out, are you familiar with quicksort? Here's how quicksort works. I know you're familiar with it, but I'm going to review it anyway because I have to continue on with the answer. So you pick a pivot. Let's suppose we pick right there. Notice that's not a very good pivot, but it's not a terrible one. And then we run through our whole list and we make sure everything less than that pivot is on the left side of the pivot and everything greater than the pivot's on the greater side of the pivot. Then we break up our list into 2 parts and we call quicksort on each part, and recursively the whole darn thing will eventually be sorted. That is quicksort. Okay, well, we'd like to quicksort this whole list, but actually we only care about this point. Do you see the algorithm forming? It's just quicksort, except every time we pick a pivot, suppose we pick that pivot, that wasn't even vertical. There's a pivot. And then when we would recursively go and sort both sides of the list, we can say to ourselves, hey, we don't care about the whole left side because the one point we care about is not there. So let's only recurse on the right side. And the next time the pivot's probably over here, but it could be over there again. Doesn't matter. And basically it's binary searching in until it finds that one point, right? And because we've got the number correct on each side of the pivot, we're still guaranteeing the position of that median point is correct. So as it happens, it's just a special version of quicksort, and it binary searches into that point until basically everything between the binary searching in, including that one point in the middle, is sorted. And if you sum it all up, on average, we're dividing the length of the list by 2 each time. So it's n divided by 2 plus n divided by 4 plus n divided by 8 plus n divided by 16, and so forth. And if you add those all up, it comes out to 2, right? Because remember the whole equation, gamma to the 0 plus gamma to the 1 plus gamma to the 2 is equal to 1 over 1 minus gamma, that one. Well, that works with the divide by 2 thing to suggest that on average, this takes 2 operations, or it takes order 2n to sort the list in this way. So it is in fact at least twice as slow as finding the mean. kind of. Well, there's a constant in there, but in fact, you have to do two things to find the mean too. You have to go make two passes. One to find the sum. No, wait, I'm talking about deviation.
No, mean is one.
Yeah, it's only one pass. You're right. Deviation's two passes, except it's actually only one pass. Oh man, I have to teach that now too.
Oh boy.
Okay, I'll just go real quick. Anyway, you get it. There you go. In C++, there's a nifty little function called nth element. That wasn't a pause for dramatic sake. That was a pause for, I can't remember the name of that function. It's called nth element. In Java, Google for nth element, and you'll find somebody whining about how the Java class library doesn't provide any equivalent for it. And somebody somewhere has written a nth element function in Java, and if you really care, you can use it. Or you can just go ahead and use sort and suffer that you're paying an order n log n price when you only need to pay an order n price. And if you're okay with that, then you're not a true computer scientist. Okay. Because all true Scotsmen care about efficiency, right? All true Scottish computer and science engineers care about efficiency. Okay. How do you calculate the variance or deviation in one pass through your data instead of two passes for your data? If you are, I guess, a person that studies asymptotic complexity would say, who bloody cares, because 1 and 2, they only differ by a constant, doesn't really matter. But just for the sake of you can, here's how you do it. It turns out that variance, while equal to the expected value of the value you get minus the mean, is also equivalent to, according to this math, the expected value of x squared minus the expected value of x squared. And so, if in a single pass through your data, you not only sum up x, but you also sum up the x squareds, then by the time you have completed that one pass, you now have collected two numbers. Now you can subtract them, and that's the variance. Then you can take the square root of that and get the deviation. So you don't actually have to do two passes through your data. Having said that, it's slightly more numerically stable to do two passes rather than one. And so it's actually better not to use this property that I just showed you. But in case you want to, now you know how to do it. Okay. Yeah. In fact, one other point while we're on this subject, one other thing you can do in one pass that a lot of people don't realize you can do in one pass is draw from a categorical distribution. And that one actually is kind of relevant to this assignment. Let's suppose your chances are 1, 2, 3, and 0.1, 0.2, 0.3, and 0.4. I picked these numbers because I just happen to remember they sum up to 1. This is a true categorical distribution, but those numbers could be anything. And let's suppose in one pass through this data, we want to draw one of those four values according to these probabilities. Now, yes?
You draw numbers from 0 to 1, keep a running total of the values of all things you looked at, and when you exceed the total, it's the one you're on.
Yes. That is the way I taught. And I think that way requires two passes, because the first pass you have to calculate the cumulative distribution, and then in the second pass you have to see which one you're greater than.
Hold on a running total as you go.
Does that work? Maybe it does. Here's my answer, and maybe I'm just going to say the same thing. But yeah, if these are probabilities, right now I'm going to draw a number from 0.1 out of 0.1. Does that make sense? Meaning, I'm going to draw a number from 0 to 1. I'm going to multiply it by 0.1. And if the number I draw, okay, what I'm trying to say is, with 100% certainty, I'm going to say, yeah, this is the one, because it's the only one I've seen so far. The total probability that I've seen so far is 0.1, and there's a 0.1 chance that this is the one. Therefore, with 100%, that ratio, I'm going to say, yeah, this is the one. And by this is the one, I mean unless I say otherwise later. So I mark this as the correct choice. Then I move on to the next item. And at this point, I have seen a grand total of 0.3 probability, right? But there's a 0.2 probability that this is the one. Therefore, with a 2/3 chance, I'm going to change my orange one from saying, oh, okay, I changed my mind. Actually, you're the one. You see how so far, if the other things didn't exist, if this were the only two, that would have been the correct distribution, right? There's a 2-to-1 chance I would have picked this one, and a 1 in 3 chance I would have picked that one. And if there was only a total of 0.3 probability, that would have been the correct distribution among them. Well, therefore, by induction, keep going down that line, and by the time you get to the end, you will have chosen any of these with the probabilities they gave. Did that make any sense? It's a thing you can do. You don't actually have to. If you just want to do 2 passes, that works just fine. But sometimes we don't like having 2 loops because it makes it bad in our code. Okay. That was kind of irrelevant. So here we are. You've coded up your Bayesian graphical model, popping all that stuff off the stack now. We're back to where I meant to be. Let us suppose you're not getting those numbers. That does mean something's wrong. How can we debug it? Here's what we want to do is first I want you to understand why these are the correct numbers. Because I think it's important that you're not just chasing a ghost, right? I mean, anybody can fiddle with code until it works, but that could take half of eternity. If you understand why this value should be 1/2, or why it should be whatever it should be. Wait, this stuff's all given. I guess we need to figure out what the answer should be. And if you can figure out the answer and you can see that your code doesn't give the answer, then you can forcibly find your bug. Okay, so let us look at the answer. For testing purposes, let us ask 2 questions of this network. What is the probability that B is true given that A and C are both true? So I'm going to say, even though I have these probabilities, what if I ignore them now and clamp them to be true? So A is clamped to be true and B is clamped to be true. What is the probability that C will be true?
It says probability B is true given A and C are true.
Yeah, oh, did I ask that? Oh, I did say that. Well, that's a harder question. And what is the probability that B is false given that A and C are both false? Okay, first thing I want you to do is don't say, hey, given that, let's just do the first question. Let's suppose A is true and C is true, what's B? You might say, hey, B depends only on A. Therefore, since A is true, there's a 2/3 chance that B is true. Is what I said true or false? The answer is false. Yes, it does say that. Yes, that's kind of what it suggests, but don't delude yourself. You know something else. You know that C is true. And you also know that C is influenced by B. Do you see how that's a hint? It tells you something about what B is. So even though B is only affected by A, B affects C, and C is known to be true. Therefore, you have extra knowledge, and don't forget to use that. I'm showing you the Markov blanket principle here, right? So it would not be true to say there's a 2/3 chance that B is true. What is the probability that B is true? And that's what we need to work through so that you can see that this is all the case. What's the probability B is false given that A and C are both false? Okay, those are 2 questions to ask. This network is so simple we can actually perform exact inference. You can actually perform exact inference with more complicated networks than this, but this one's, if you're going to debug, you want a darn simple one, right? Okay, so to answer the first question, we compute the probability of B is true given that A is true and C is true. You see how that says the question is proportional to 2/3 times 1/2. Okay. Do you know why? Why 2/3 times 1/2? Look at what we're saying here. It's that 2/3 number, which is the conditional probability that B would be true given that A is true. And we've multiplied it by 1/2, which is the conditional probability that C is true given that B is true. Why did I do that?